just asking you to try and sit somewhere in front. Oh, yes, okay. Does that make sense? Yeah. I was told about that. Natural science. Yes. Good morning, everyone. I feel slightly silly with all these in front of you all, but it said encourage you all at the end. We're going to take some questions and also take questions throughout. And if you'd like to ask these questions in Welsh, please feel free to do so. We do have someone providing translation for everyone. Thank you very much. Okay, I was going to say I do feel slightly silly with one of those at the front. Right. Good morning. What's everyone expecting from a natural sciences lecture? Nothing? Any kind of subject? Any kind of topic? Does this mean anything to anyone? Thermophilic chemistry? Well, I'll go through that as we go through, but first to introduce a little bit about who I am. As it says on the side, I'm Luke Williams. I've just completed my PhD at the University of Bath. Before that, I did my undergraduate at the University College London, where I studied biochemical engineering. I'm not going to go too much back into my background, but if you do have any questions about either of these universities or the subjects that I'm going to discuss today, I will be around the exhibition hall this afternoon. Okay. So, we'll start from a point of sustainable development. So what is sustainable development is what we're going to cover to start with. Look at the energy sector as an example of something that you probably have come across and studied before, just to give you a flavour of the kind of direction I'm looking at. And then looking at the sustainable chemical industry as a whole, not just the energy sector, expanding it to things like biofuels, plastics, that kind of thing. And then finally, looking at the topic of thermophilic chemistry, and how that might assist the transformation into a sustainable chemical industry. So, Anyone have a definition of sustainable development? Anyone come across one? Anyone have a personal example?
Development that doesn't involve any economical damage or environmental damage.
Yep. Any other examples? No? Okay, well, there is a very famous example, definition, and this was done by Gro Brundtland, who was the Norwegian Prime Minister for the United Nations. Said is development that meets the needs of the present without compromising the ability of future generations to meet their own needs. It sounds quite a clunky definition, but no one's actually managed to get a more succinct summary sort of that actually covers all the points. But there's an alternative way that you could look at sustainable development. You could look at it in terms of the 3 pillars, as the previous definition, and that one. So you're going to have the sustainable part of it has to include all 3 elements. And by social, what this means is sort of general acceptance with the public. So controversial issues at the moment, for example, might be genetically modified organisms. That's been quite controversial for some time. The environment, so mining is considered to be one of the stereotypical things. Mining destroys a large area. Oil fields, fracking is also quite kind of a topical discussion. And the economic, there's no point trying to do something if you're not going to be able to continue doing it because you're losing so much money, your business will collapse. And this is not just true for commercial enterprises. This is also true for charities and non-profit organisations. They can't keep losing money. There must be some way that they can keep going to pay the people that work for them and that kind of thing. So, a little bit of engagement here. Is renewable energy sustainable? So I've got a few examples here, starting from solar. Quick straw poll. Hands up, do you think solar panels and solar power in general is sustainable? Quite a number of you? Most? Anyone think it isn't sustainable? A couple of people willing to just, I would argue that solar power isn't sustainable at the moment. Economically, it's producing power at roughly the same rate as fossil fuels. Obviously, using reliance on the sun, there's no problems in the production method of the energy, i.e. you just leave the panel out there, it gives you your energy. But the actual production process of making these solar panels is very involved at the moment. So for example, one of the most common types, so you have silicon types of solar panel. These are okay, they're still not great. They're also easily recycled, which is a big bonus. Other types, which are more efficient, are made of things like cadmium telluride, both of which are very rare elements. There is some work going on at the moment to try and make them from organic dyes, which is obviously going to be a much better way of producing these things. But there's still a number of layers in the solar panel which can cause issues and are required in order to harvest the amount of energy from sunlight that is kind of needed to make them economically viable. Wrong way. Another one. This is wave power. So some sort of snake. Another example. Sustainable? Hands up if you think yes. Fewer this time. I'd say it probably is, but we don't know really where this technology is going to go. I've not actually heard any concrete examples of this being in commercial production. It might just be something that goes to a dead end and never actually takes off. I don't know yet. Hydrothermal. Hydroelectric. Dams. Biggest of being like the Hoover Dam. Sustainable? They last a very long time, but they also got to think about what they're made of. Concrete. Huge, huge, huge amounts of concrete. And concrete is one of the most substantial CO2 emitting products that we produce. So you've got to think very carefully, because that, as I say, it's a truly astonishing amount of concrete. millions of tons of stuff. And another example here, wind. Who thinks that's sustainable? No? Well, there are a couple of issues with wind, as you might have guessed. The biggest problem is the magnet inside which you need to run the turbine. It's made of neodymium. Now, if we wanted to convert all our power supplies to wind energy, we couldn't, because there's not a large enough supply of neodymium in the world. That's the kind of issue that we have problems with when you think about sustainability. Now, it's not just up to me to say whether these four are sustainable, and it isn't good enough just to say where something is or is not sustainable. There is always a gradient of sustainability. You have to interpret these things based upon the purpose you're looking at them for. So, in this case, we're looking at them in terms of, are they better than fossil fuels? And in many cases, that's pretty easy to say, well, yes. They don't produce the same amount of CO2. But CO2 is only one of many things which could affect the sustainability of a given process. So you have, for example, the footprint. So these are good because they're out in the ocean, that's fine. The thing that's often thrown at wind is that it kills birds. Well, yes, it does. But more birds die from coal than they do from wind and gas and these kinds of things. So, yes, they do kill a few birds, but they kill many less birds if they couldn't have power than a coal power station. So, there are ways and sort of swings and roundabouts on that. So, where this all leads is to the idea of life cycle analysis, where you don't just consider your production. Where, for example, in solar power, the sustainability is not just governed by, well, we've built the panel, we've installed the panel, and now it's producing energy for the next 25 years. You have to think about the production of your item, or product, or service, the transportation involved in that, and later on, sort of the packaging it comes in, the shipping, the use, which is the one most people just think about, but we're at the recycling, and then back to the raw materials. So all these kinds of steps are quite involved, and the biggest problem with many of these technologies is that the information and data required is simply not available. You've just got to look a bit more closely at it, maybe have someone look in more detail about how long these things, how involved is the process of making a solar panel, how much of the materials do you use, what is the wasted streams from all these things, and these aren't always immediately obvious. So where that leads is to the idea of sort of a larger, more involved system where you think about the sort of where the life cycle of natural organisms goes from sort of natural decay, extraction, materials recovery, sort of this kind of cycle powered by renewable energy. And then what we have to sort of look at is, sort of, as humanity itself, is to see how we can sort of do these kinds of brown arrows. So instead of just having the materials and doing some recycling, so when you produce something, there's always some sort of waste in the production cycle. So what you can then do is think, well, take about the waste streams from the production cycle and move them round. Or if you're recovering materials, either after you've used something or so in this case, you're going back to materials, so if you recycle something like glass bottles, that kind of thing, you can recycle them, reuse them. That's kind of what generally is considered the best way to do things. But also, if you go further than that, and actually make something new with the materials you're using, that's what remanufacturing is. So taking your glass bottle, breaking it down, smashing it up, and making it into a new glass bottle, that's sort of remanufacturing. And the reason you would do that over something like recycling or reusing, more to the point, is because perhaps you're looking at filling it with something different. Maybe you're looking at something which is biological hazard, for example. So you can't just reuse the same container, you've got to do something to it, sterilize it, or completely remake it. And these kind of examples are not just isolated to things like glass and plastic and things. This sort of includes things which are much more complicated. So things like washing machines, chairs, any kind of product and service that you can think of that has to be produced. There's an element of what can we do to this production process? And then you've got obviously reuse, dispose, and kind of recycle again. Now, the way this goes, if you take it a step further again, is something called the circular economy. So this concept is instead of making something, using it, getting rid of it, you think about, well, what can we do beyond that? How far in this cycle can we get? And the easiest way to sort of go through that is, I have a short video here, which will explain it slightly better for you.
Living systems have been around for a few billion years and will be around for many more. In the living world, there's no landfill. Instead, materials flow. One species' waste is another's food. Energy is provided by the sun. Things grow, then die, and nutrients return to the soil safely. Yet as humans, we've adopted a linear approach. We take, we make, and we dispose. A new phone comes out, so we ditch the old one. Our washing machine packs up, so we buy another. Each time we do this, we're eating into a finite supply of resources and often producing toxic waste. It simply can't work long term. So what can? If we accept that the living world's cyclical model works, can we change our way of thinking so that we too operate a circular economy? Let's start with the biological cycle. How can our waste build capital rather than reduce it? By rethinking and redesigning products and components and the packaging they come in, we can create safe and compostable materials that help grow more stuff. As they say in the movies, no resources have been lost in the making of this material. So what about the mobile phones, fridges? We know they don't biodegrade. Here, we're talking about another sort of rethink, a way to cycle valuable metals, polymers, and alloys so they maintain their quality and continue to be useful beyond the shelf life of individual products. What if the goods of today became the resources of tomorrow? It makes commercial sense. Instead of the throwaway and replace culture we've become used to, we'd adopt a return and renew one, where products and components are designed to be disassembled and regenerated. One solution may be to rethink the way we view ownership. What if we never actually owned our technologies? We simply licensed them from the manufacturers. Now, let's put these two sides together. Imagine if we could design products to come back to their makers, their technical materials being reused, and their biological parts increasing value. And imagine that these products are made and transported using renewable energy. Here we have a model that builds prosperity long term. And the good news is, there are already companies out there who are beginning to adopt this way of working. Now, the circular economy isn't about one manufacturer changing one product. It's about all the interconnecting companies that form our infrastructure and economy coming together. It's about energy. It's about rethinking the operating system itself. We have a fantastic opportunity to open new perspectives and new horizons. Instead of remaining trapped in the frustrations of the present, with creativity and innovation, we really can rethink and redesign our future.
So, where do I kind of fit in with this? Why are we doing this is another key point. Well, these kind of resources that it was kind of referring to are, at the simplest level, a load of elements. Now, do any of you think that we're running out of any elements? Have you heard of any elements? Yep. that we're running?
We're running out of helium, I believe.
Helium, that's a very good one. Mostly because we can't store it. And the US government is selling off very cheaply. Any others? Do you think we're going to run out of any materials in the next decade? Well, quite a few, in fact. All those in red, at current extraction rates between 5 and 50 years, it's believed that we'll run out of useful supplies of those materials. And you might think, well, hafnium, I can't remember the last time I used any of that. You know, okay, well then you've got gold, silver, platinum. You know, no more jewellery. We'll never run out of enough materials to have no jewellery, but you know, the price of these might go up. But then that will obviously encourage more people to go mine for more of these materials. But there will come a point where you have to look at, you know, is it economical to do so? I do know that in Japan, for example, they're actually mining their rubbish tips for metals because there's a higher density of some metals in their rubbish tips than there are in their mines. And this is from things like phones and other electronics. So that's quite horrifying, at least to me, when I came across it. And as you might notice, you've got all the lanthanides are kind of on notice as well. And again, you can just say, well, these, well, okay. Surely you only use a little bit of it. Why do we care? Well, some of the example uses. Most of this can be summed up in modern technology, electronics, the iPhones, or Android if you're that way inclined. So particular examples I'd like to raise: flat panel displays, batteries, steel, I think a little bit niobium used in some high-strength steels. For my interest though, it's palladium, platinum, and sort of rare earths, rhodium, ruthenium. The reason being, all these are used for catalysts, industrial catalysts, which are incredibly useful, necessary for kind of the current level of technology that we as a society have become used to. Without them, your medicines are not made. Your plastics may not be made. Electronics, well, they're probably better off, but you know, there are more other things. But most of these things, you know, fuel cells are a new technology. Catalytic converters. Boris Johnson had the bright idea of hoovering up London's roadways because of the catalytic converters kicking out all the dust of platinum and palladium. He was kind of laughed out of the town, but you know, it is something that could be done because there's a very high quantity, comparatively speaking, of these metals on roads, particularly busy roads, because of the catalytic converters of cars which spit out these elements into the road. So, if we didn't have these sort of metals around, then we as a society would be completely different. I wouldn't be able to give this presentation, for example, because of the equipment that requires these metals. So we have to think, as a society, where are we going to get these materials from, or if we don't have access to these materials, how are we going to do the necessary chemistry that we need to do? So this led sort of in the 1990s to the principles of green chemistry, where 12 principles were laid out. There's the first 6, to have a sort of general idea about how we go about designing better chemical processes. And this is the kind of area that my research centre for my PhD was involved in, the Centre for Sustainable Chemical Technologies. So I had colleagues who were looking at solar panels, colleagues who were working at wind turbines, looking at water quality, all these kind of different things, looking at to see how chemistry could be used better. Does anything strike you about these kind of ideas? Any questions about those ideas? Comments? Well, it's easy to say some of these things like prevention, prevent waste. You know, some of these processes, new processes that are designed, you aren't going to be able to put all these kind of ideas into. Generally speaking, when you do research in a lab, you do something that works, and you try and worry about these things later. That's a problem, because by the time you started, as we'll see, I'll be going through a process shortly. It can take quite a substantial period of time to redesign your process into something that's greener and uses up less materials. So, what these kind of general ideas, you can kind of characterize them. So, safety is one group. So, solvent safety. Some of the more toxic solvents now are simply banned. A good example there is carbon tetrachloride, which will essentially give you cancer if you look at it wrong. Whereas, so another example would be benzene. Benzene used to be used as for shaving in the 1900s. It's cancerous. It will just give you, it's carcinogenic. It just, yeah, it's not great. So, how do you transfer processes that use these kind of solvents and into something that's at least marginally useful? So they, for example, carbon tetrachloride moved on to things like dichloromethane to just remove the number of chlorines. Still not a great solvent, but it's just slightly better than other stuff. And some of this is about the small steps, particularly when you're talking about processes that could be such a large scale to be in the millions of tons of product. The small steps really do add up. So yes, safety is obviously one of them. Energy usage is probably another, and then your actual chemical kind of process itself. So is there an alternative method of making this that starts from a different material? This kind of thing. And the rest. So renewable feedstocks, that's where chemistry can come in a second. Catalysis. Surprisingly enough, not every process uses catalysts, particularly at research scale. People don't think very much about just chuck in a load of that, it'll be fine, it'll work. I've done it myself. Des Martin oxidation, because I'm not really a chemist, don't really know too much about details. So I said, it's fine, just use this stuff, chuck it in, mix it up, be fine, done in an hour, job done. Molecular weight of Des Martin catalyst, not catalyst, Des Martin material is about 600, and I needed it for 2 hydrogens. And then you chuck the rest out. So that kind of stuff is often used because it's simple, it works every time. You don't have to worry about it. You literally just, when everyone says something about chemistry, you just think like, witch for the cauldron. Literally this kind of thing. Chuck all the ingredients in, mix it, job done. Filter it. So that kind of thinking is still endemic in chemistry. And even at industrial scale, that kind of thinking still will be there. If it's cheap enough to do, they'll do it. A lot of companies are changing, but there's still that element there that needs to be considered. So the circular economy does come in, things like design for degradation. Not everyone thinks about chemical products in the same way as a physical product. So for things like medicines, drugs, both medicinal drugs and recreational drugs are building up in the water supplies of this planet because the current sewage systems that we employ cannot get rid of them. So it's starting to get to a level where it's affecting wildlife, it's affecting human life and human health. And you'd think, with the amount of water available on this planet, it would take a while to do that. Unfortunately, things are building up to a concentration that's starting to get pretty nasty. The obvious example that tends to be given around is hormones that are affecting fish and things like that, affecting their life cycle. Could be having an effect on human health. Who knows? People need to investigate this, and some of my colleagues were looking at water quality. So, go a bit further, mind you about chirality. I presume these sort of things a little bit familiar to you. I've recently been teaching chirality to some year 9s who looked at me quite blankly. So, chirality, everyone happy with that? Not cover chirality? Okay, I've clearly missed the syllabus. Right. An introduction to chirality. The definition of a chiral molecule is this thing called a chiral center. It's got 4 different constituents on it, 4 different atoms or groups. Doesn't matter what they are, any of them. Because those 4 are different, what happens is although they have the same atomic kind of structure, they'll actually have different chemical properties. So, identical to the diagram showing hands, if you think about it, your hands, you cannot put one on top of the other without flipping one of your hands. So they have a mirror image, and the definition of these molecules is that they are non-superimposable mirror images. Okay? Now, you might think, okay, this is kind of cool, but again, what's the point? Well, the point is, unfortunately, people can die if you get this wrong. The most widespread example of this was from the 1960s in the case of thalidomide. Thalidomide was a drug that was used for pain relief, to help sleep, that kind of thing. It was also discovered it was great to treat sickness, in particular morning sickness, given to pregnant women to treat morning sickness. Very well it did that. Unfortunately, one variant treated morning sickness, the other harmed unborn children. So you ended up with, unfortunately, a lot of children, for example, with missing limbs and quite substantial alterations because of this drug. And this is why this sort of now, if you want to market a new drug, you have to ensure that you're only producing one type of your particular medicine, or you've proven that both types are safe. More typically what happens is that one of these types just doesn't work compared to the other. Not that they're always toxic, but it just happened in this case this was. And it was particularly unfortunate in this case because they did recognise this. The problem was they produced one form and the body was able to convert it from one form to the other. So it doesn't actually matter in that particular case of thalidomide which type they gave, it would still have caused problems. But it's still being used today, thalidomide. It's not generally used in the Western world quite so much, but it's still often used, I think now being looked at as a treatment for leprosy. So it's got around, but you've still got to be very careful with it. So what I'm going to run briefly through is one example of how a green process can develop. In this case, it's sitagliptin, which is a type 2 diabetes treatment. So this is the original process diagram for sitagliptin. Now, I don't really want to go through the nitty-gritty of it, but what I do want to do is draw your attention to a few key issues. So to start with, the first process here, this uses ruthenium, hydrogen bromide, triphenol phosphine, which in itself is used as a chemical warfare agent. And you've also got 1, 2, 3, 4, 5 steps. Not particularly long as chemical processes go. 10 steps is also, perfectly reasonable. So, and palladium and carbon, of course. Every good chemical process uses platinum, palladium, and carbon. It just does everything that you want it to do, more or less. So yeah, great process, seems all right. But look at the yields, 83%, 81%, and 78% from sort of there. Multiply those together, about 51%. Not great, is it? 51% product? Would you be happy with that kind of level? And as I say, it uses ruthenium, it uses palladium, it uses some fairly nasty chemicals. So they went away and had a look at it, and they came up with this. They started from a different starting material. They also did one pot. So that means you don't have to worry about isolating your product, and that is where the big issue tends to come. It's not the fact that you're producing something and the process isn't particularly efficient. It's always your effort to try and get it out, and I can speak from personal experience. You can lose quite a lot of things. As I said, I'm not a great chemist. I'm more of a biologist. But I've done a little bit of chemistry, and that little bit was plenty enough, thanks. I can't filter anything, really. I get some quite interesting comments from some of my colleagues about how simple it is and how idiotic I must be. But even if you do it well, you still end up losing some of your product, even if it's only a little bit every time. So this is why one-pot things are excellent. And more to the point, some of these things, catalysts, you know, ammonium acetate, that's a little bit better. Still got some rhenium sleeping in there now, and carbon treatment for rhenium removal. Remember, this is a drug, you can't have metals in your drugs. The limit for metals is incredibly low. I mean, sort of annoyingly low if you're trying to remove it. Because obviously, if you're giving these pills, or even worse, injections to people, you can't be injecting them with metals. They're all toxic. I think other things I'll draw your attention to. So 81% yield, 98, that's really good. So 98 from there to there. Sorry, 82 from there to there, 98, and then 81. So that's, a fair bit better. Also, by the end, these are important. The purity of your product, obviously very useful for medicine, kind of critical. There are many other things. The EE is called the enantiomeric excess. This refers to the chirality of it, i.e. how well they've been able to extract and just make sure there's only one enantiomer. For chemistry, this is quite difficult. Many cases, this is why you have this particular rhenium here, is to ensure that your catalyst is able to make one form of that. It is difficult, it uses very specific catalysts, can be quite tedious. These are the kind of reasons that you might want to look at enzymes, which I'll come on to very shortly. And that's something I love more, enzymes, biologists, yeah. I get strange looks in the chemistry department. Anyway, third stage, they changed to a ruthenium thing, so from, oops, hang on. So these arrows here are where we're coming from here. Slightly changed it, slight improvement, higher yield, higher ED. Again, ruthenium. So they thought, we'll use an enzyme. So they did. They replaced this bond part with even greater ED, and this is actually quite good. You think 99%, surely that's good enough, right? No, unfortunately not. 99.5 is kind of a good. 995, sort of great, but they'd want higher if possible. And then just acid. So why am I showing this one? Well, this particular process, this was what they started with. This won a Presidential Green Chemistry Award in the United States because it was so good an improvement. And they went, you know what? Nah, we're still not happy. Went again, won another award for this, then another award for that. So they like collecting awards. Anyway, the point of this is, this was not off-the-shelf enzyme. This enzyme had 14 mutations put into it in order to make it more efficient for the task that they wanted. So, another thing you need to get across is enzymes aren't great from the start. Natural enzymes tend to be very, very good at what they're meant to do. They're meant to be in a cell where there's a huge amount of protein, where there's a very low concentration of the chemicals that they're transforming from one thing to another. In industry, if you were trying to work at the kind of dilution levels that a normal enzyme works at, they laugh at you. It's just not enough in there to make it economical as a process. So, you need to make it happier with the concept of hundreds of grams per litre of their material. You have to make them kind of more stable. These kinds of considerations, which are a little more difficult. So where do I come into all this? What have I been up to for several years as my PhD? Well, I work with this thing. This is Geobacillus thermoglucosidaceus. It's a species of bacteria that you normally find in compost heaps, and it's currently being used to make bioethanol. So what they do is they take kitchen waste, that kind of thing. This will use that, break it down into glucose, feed on it, and produce ethanol. Wasn't really kind of looking at that. What I wanted to do was use the same organism to do this kind of general reaction. Are you familiar with squiggly bonds? just means both enantiomers. So both types of those things. It's just a notation. So just forms a ketone to an alcohol. That's the one reaction I was looking at. Kind of the secondary one was an aldehyde to an alcohol, but effectively the same reaction. And use the same enzymes using that reaction to look at pharmaceutical intermediates, bioplastics, anything that was kind of a higher value than ethanol, basically, because I found ethanol a little bit boring, as I was quite often to tell some of my colleagues who were working on it. I tend to get hit a lot for that kind of discussion. So that's where I come into all this, and that's what was my little piece of sustainability argument. So one important thing about Geobacillus thermoglucosidaceus, as the thermo in its name kind of implies, it works at higher temperatures. It likes to grow at about 60 degrees, although it will be happy up to about 70. If you had it at room temperature, it would quite swiftly die because it can't cope with such a low temperature. So what's the advantage of working at higher temperatures? Higher rate of reaction, generally speaking, although slightly less so than you'd think, simply because enzymes from different organisms that are kind of similar in terms of their reaction are typically optimized to work at specific temperatures. And this, so for example, a thermophilic organism working at a thermophilic temperature is probably about as efficient as one working at normal temperature if it was in an organism that tended to grow at that temperature. So you don't always get the huge advantage that people seem to think you do. Improved operating conditions, I'm thinking about viscosity and things like that. Things flow a little bit easier when they're a bit high. Reactions that are thermodynamically unfavourable suddenly go, oh, okay, I'll work for you. You know, things get a bit better. Reactions might get, the balance of equilibrium might shift as well. Chemically resistant enzymes. There's been a correlation noted between enzymes that work at higher temperatures and enzymes that work in things like organic solvents, simply because the same sort of modifications that will need to exist at these kind of conditions makes it compatible. So higher temperature is great because you can just dunk it in ethyl acetate and it'll work for you, which is great. Reduce contamination. Yeah, so if you've got something growing at 37 degrees in a tank, E. coli go, oh, yeah, that works for me, thanks. I'll come live in. If you're not careful, yeast, whatever, will just go, huh, it's a lovely bioreactor you've got there. It'd be a shame if something happened to it. And that can ruin entire runs. And when I say an entire run, I mean sort of a reactor the size of the room. You know, so if one of those runs sort of goes south, you're talking thousands, tens of thousands, maybe hundreds of thousands of pounds lost. So if you're working at 60 degrees, okay, you can still be contaminated by things that look at 60 degrees, but they've got to get there. It's slightly more difficult for them. And if, for example, Geobacillus tried to actually contaminate something, it's got to get from wherever it is to that tank without dying, which for Geobacillus, if you look at it wrong, trust me, it dies. And you can assist by removing volatile products. So what the company I was working with had sort of a vacuum pump kind of thing at the top. So what would happen is they were looking to produce ethanol. 60 degrees, the ethanol would kind of be volatile and go off, and they just hoover it up whilst they were going. So I was hoping to sort of use that kind of similar system to do that kind of thing with chemical products, which is a bit different to how chemists do it.
Where would enzymes like this occur naturally?
So Geobacillus lives in compost heaps. It's found in soils across the world. It's one of the ones that will actually degrade your compost for you. But Geobacillus species have been found in oil fields, they've been found in the bottom area, in the trench, everywhere really. People just don't always look for them. And also it's worth pointing out that a lot of new species that are being found are actually not cultivable. We can't grow them. Let's try that. The reason being we've not found why they don't grow yet. You know, you can put a lot of species on an agar plate and just let it go, but most of the time, about 90% of known bacterial species we cannot grow. We don't know why, as a general group. So, whiz through a couple of these chemicals. We're told I've been rambling too much. These are the kind of things I was looking at. the interesting one here is the raspberry ketone. So most reactions want you to go from the ketone to the alcohol because the alcohol is the thing that's chiral and that's kind of useful. Raspberry ketone, it's actually want the ketone. Raspberry ketone from the name does come from raspberries. 3.7 milligrams per kilogram of raspberry. Raspberry ketone is also one of these newfangled diet drugs. Lose 63 stone in 10 minutes by taking 3 pills of this, that kind of thing. People want the word natural on their product. By EU law, you cannot have a process that's modified chemically called natural, but you can if it's done biologically, even though it's the same reaction. So that's why that one is up there. That's why I was looking at that. It's a bit silly, but it's the way it is. I will probably skip my research approach. There is my uses on an SDS page gel. You come across gel electrophoresis. Literally just put electric charge on the proteins and have them run down the gel. Yeah, that was my PhD in one picture. Hey. Gotta plug it somewhere. Right, chemurgy. So what is chemurgy? Chemurgy is a branch of applied chemistry where you're looking to extract chemicals from natural resources. In this case, things like agricultural specifically. So very briefly, traditional route, oil. Everything comes from oil. And then you might have some sort of new process, biological process, and then some sort of traditional product. Alternative approach, things like lignocellulosic material, forest waste, that kind of thing, could be plugged into chemical kind of traditional processing, and might end up with a novel product at the end of it. So this bit here is the chemurgy. So, something like this you might have seen before. We're looking for is the kind of map-making chemicals point. And kind of a new way of looking at it is to look at the biorefinery. So a huge kind of breaking down into different parts. Try to replace oil with forests, basically. And that's chemurgy, in a nutshell. So all these kind of different types of materials be able to grab from biological sources rather than oil. And really is it. Thank you very much. Any questions? We've got 2 minutes for questions. I have kind of gone through a fairly large amount of material, but biology, chemistry, I can do engineering at push too, but I'd like to stick to natural sciences, and that's why I'm here. Anyone have any questions on this subject or anything to do with university?
Yeah, you know the metal that was in the wind turbines?
Yep.
So is that the only metal you can use for that?
No, but that's the one that's used at the moment. The reason for that is it's most efficient, I think. But yes, we'd have to consider using other metals and taking a hit on the efficiency of it. Or recycle them, but again, we can't have too much. Then you get the idea of balancing the load on the power plants. Can get a bit more complicated than that, but I think that's it. Anything else, anyone? Biology, chemistry? Everyone have enough? Run off to somewhere else? All right, thank you very much, guys.